I'm happy to welcome every one of you to our FAIRWork webinar today, which is the 10th in our series and the first in 2024. This was firstly scheduled to be in December, but unfortunately we had to postpone it. But now we can all restore it after the holidays, hear this interesting webinar about this AI enrichments. It's about the FAIRWork project, so I will just give also a bit of context because the presenters, I don't think, go into these details because they focus really on this AI part, but we want to do decision making in production environments, so in complex environments, and the colleagues from RWTH Aachen, Sylvia and Alexander, will now present us how AI can help us with this and which AI algorithms can we use. And if you're interested then in FAIRWork in general, you can also visit our webpage, which has all the recordings of the other webinars. But I think now I have talked enough, so therefore I gladly give over to Alexander Sylvia that they can start with the interesting webinar. Thank you.
So thank you, Christian. So before we dive into how we apply AI in FAIRWork use cases, I want to talk about some selected terms in AI in general. So just a rough classification of terms. Artificial intelligence is basically an umbrella term and pretty general term, which describes all kinds of algorithms that yield some kind of intelligent behavior. Later on, we will see all of different algorithms and how they work. And there is the other part of artificial intelligence, which is, or not part of artificial intelligence, but a term, data science, which is pretty adjacent to that. And data science is more about just working with data, finding patterns in data, applying statistical methods, which not necessarily have to be AI methods. So, and then there is a overlapping category of which is machine learning, and machine learning is basically doing artificial intelligence with data-driven methods. And exactly this field here, so machine learning in recent years has become a driver for a lot of innovations and interesting algorithms. And machine learning itself can be further divided into these three categories. So that is supervised learning. Supervised learning deals with data where you have labels, so annotated data. What you can also do is supervised learning. So when you have data that is not labels, and this is more about finding patterns in data. And then there's reinforcement learning, which is essentially just learning from interaction with an environment. Today, we will have a bit more details towards supervised learning and reinforcement learning, and we will not talk so much about unsupervised learning here. So let me quickly go over what you could do with supervised learning. So the first thing you could do with supervised learning is regressions. So suppose you have a bunch of data. So here X1 and X2 map to Y. This could be like any maybe physical pattern. So I don't know, just if you have measurements of water, like for pressure, temperature, you could measure density, for example, that could be represented by such data points. And what regression now is doing, it maps a curve through all the data points you have. So it finds a parameterization for a curve. So all you do is basically you estimate a function. And this function in here is just, let me just grab the laser. Whoops. So I wanted to grab the laser pointer here. Here we go. It's just a parameterization for this curve here. So this could be a neural network, a decision tree, but the key component of supervised learning is just approximating a function. So another thing you could do with supervised learning is classification. So suppose you have a bunch of apples, a bunch of oranges. For these objects, you can measure some features, for example, here, weight and size. So just take the diameter, put them on a scale, read what's written on the scale, and plot the data points. So the red ones here are apples, the other ones here are oranges. And the function you would approximate in this scenario would be just a decision boundary which separates the class of apples from the class of oranges. So again, in the end, you approximate a function, which you then can query for new data points. So if you give it a data point, it will tell you if it's an orange or an apple. So then let me quickly go over reinforcement learning. Reinforcement learning is pretty similar to a human playing a video game. So in reinforcement learning, we have an agent interact with a so-called environment. So, and you can think of it, so when you're playing a video game, you as a human just look into your TV, you have a controller, you press some buttons, and all the magic happens in the console. So in a reinforcement learning setup, when the agent interacts with an environment, so you have basically three key parts that you have to tackle, which is once the action space. So this is roughly speaking, which buttons you can press. So which buttons do you give the agent to be able to press? Then the environment itself encodes all of the dynamic of whatever your problem is. So it could be thought of as of the game console with the game. And then the console reproduces a signal, here the state signal, which you can think of just an image on the screen, which the agent later on uses to come up with the actions. And for the actions, the environment grants the agent also a reward. So this is basically a score of how good you play the game. So in most old Atari games, you always have like, or most of the time have like a score counter in the upper left corner, or for example. So with these methodologies, you can solve all kinds of problems. And we'll go now into some applications and some use cases we tackled.
Thank you, Alex. So here I will use a really nice introduction of Alex to reinforcement learning to show it in inventory management. It was one of the possibilities within FAIRWork project where we could investigate reinforcement learning. And what we wanted to optimize here, it was the prediction, it was the ordering of the material. So the aim of the ordered material within the warehouse. So why it was important, why it is important. When the production site has a demand for certain materials, they are, in our case, asking warehouse for the available materials. So the warehouse needs to meet the demand of the production site for the certain productions. If the demand is not fulfilled, it can cause even it can cause first as a slowing down of the production, or even a stopping it, or need of the rescheduling. So everything that I mentioned, it's really costly, and we would like to avoid that. Reinforcement learning can be exactly used here to optimize the ordered amount of the materials. Taking as a base the introduction from Alex, here the agent can be a human that it's ordering the material, a certain amount of the material that it's later on delivered to our environment, so our warehouse. The warehouse then sends the material to the production site. So what is happening here, and what is our reward? Our reward is the amount of the material that was used, that was sent to the warehouse. It was sent to the production site. I'm sorry. However, how we wanted to add additional penalty because we wanted to avoid having money on the floor. So the storage in material that it's not used over a longer period of time, as well as we wanted to avoid shortages of the material. So we wanted to avoid not fulfilling the demand of the production site. That was included in our penalty. The state in our case, in this case, is an inventory level and a day of the week. Why as well day of the week? We wanted to add this, and we also over the whole year added the seasonality that also shows that some items maybe are produced more often during the summer, and during the winter less. So we wanted also to adapt this particular thing. And this information are later on fed to the agent, and so on, that reinforcement learning can appear. The next example that we were working on is genetic algorithm used for resource allocation. So the resource allocation in our case here, in this particular case, it's the pairing of the worker to the machine. So genetic algorithm is a method for solving both constrained and unconstrained optimization problems. And it's based on the natural selection process that mimics biological evolution. This algorithms repeatedly modifies population of individual solutions. And we applied it exactly in the worker allocation scenario to create a tool that gives recommendations for the end user to match worker and machine together. The program computes the total scores and proposes optimum pairing by taking into account worker preferences or features like machine capabilities. So we believe that it might be pretty useful. And one last but not least, we also tackled the test building use case, where it's about the design of the working station where the human works together with the cobot. For that approach, we used the analytic hierarchy process as well as fuzzy logic. What it was about. In order to have a successful design for working station, safety is a really important aspect, as well as the efficiency. Because why would we design in a certain way if it's not efficient or it's not safe for a human that it's operating together with the cobot? So taking this information into consideration, we applied AHP to calculate the safety ranking, and the fuzzy logic, the efficiency rating. Giving a little bit of background, the AHP helps to prioritize and make decisions in complex situations with multiple criteria that can be defined in a concrete way. It includes mathematical computations to derive a set of weights that reflects the priority of each of criterion or alternative in relation to each other. And these weights are then used to aggregate the criteria or alternatives and to make the final decisions. So it's a little bit more than only a human could do. We could come back shortly to the previous slide, because I wanted to as well say a bit something about the fuzzy logic that handle why we use that one in terms of the efficiency rating, because it handles the imprecise and weak information. So let's say we will have something like high, low, hot, cold terms, and it can quantify it in a manner that we can use it later on and apply some weights, and having a certain degrees of the certain degree of the rating, like between 0 and 1 as well. So what was popping out here in case of this application? We had a dynamic switching window popping out, where the user can rank or describe many elements, like the cobot cell setup, layout, robot movement pattern, gripper selection, which was like adjust to the cobot. So here's like a playground for the end user to like check it out with what features, what efficiency and safety rating the person will get at the end. So that would be all from my side, and I'm handing over to Alex.
So thank you, Sylvia. So in Sylvia's part, we already heard about a genetic algorithm for mapping workers to machines. And I want to quickly go over how one could extend this use case. But before we go and do that, I would like to recall some key properties of optimization problems. So the key building blocks of an optimization problem is that you have a problem instance, decision variables, constraints, and the objective function. So maybe an example that everybody could relate to, suppose you want to get from Cologne to Berlin. So just finding a route from here to there. So it doesn't have necessarily to be like from Cologne to Berlin, but it could be, I don't know, from Vienna to Rome. So that is a problem instance. So how do I get from here to there? Then you have to somehow define decision variables. So in that case, it could be, yeah, which roads do I take and which ones I don't. Then maybe you have some additional constraints, like maybe you don't want to drive over highways and avoid high speeds. And then you, of course, also need an objective function. So maybe it's you prefer having a fast route. Maybe you prefer just, I don't know, have a nice view. So these kind of things are the building blocks. And first of all, I have a very small nurse scheduling example. So suppose you're in a hospital, you have 4 nurses. Nurses work 3 shifts a day, and you want to plan for the next 3 days. So this would be then your problem instance. So for nurses, 3 shifts a day and a number of days. That's your instance here. Then you come up with the decision variables. So this decision variables in this case could be just a Boolean variable. So 1 or 0 if a nurse is assigned to a specific shift. So nurse to a specific shift on a specific date. So these would be just a bunch of tuples that you want to find values 1 and 0s for. Then your constraints would be maybe that you cannot work like only 1 shift a day and not 2 subsequent shifts. So not after the night shift, maybe directly in the morning. So that you could encode like here. And then when you put it into a general purpose optimizer, like a mixed integer program, you would get a solution like so. But in real life, things are a bit more complicated. And for the allocation process in the production hall, what one could model this problem in the CRF use case is, so we already had a look at the worker allocation. But what you can also take into account during the optimization is in which points in time do you process which order on which machine. So I think this could be pretty well modeled as a flexible job shop problem with some additional constraints that are problem specific here. And then for the allocation of the orders in time, do the worker allocation on top. So how does it look like? It could look a bit like so. So in here, in this 2-layer process, you would firstly come up with where do the orders are allocated in time. And then in the second step, you would allocate workers. So the boxes in here represent orders, and the colors encode machines. And first in the first layer, your problem instance would be just a bunch of orders, and then it would come up with a schedule. This is also called a Gantt chart. And then for the Gantt chart, this would be the problem instance for the layer 2. Together with availabilities of workers, you would come up with an allocation of these worker dots here for that Gantt chart. So this is like a 2-stage process you could model this as. You could also do it in 1 step, but this would also be much more complicated. I think it is pretty reasonable to do it like in this way, so you can also mix and match different approaches here. So, and one specific method that I think could be really, really useful for such a thing, for such a problem, is the Monte Carlo tree search, which is used a lot in games and planning games. So where you look ahead and plan on which move to do. So a very basic example could be here a tic-tac-toe game. So suppose you are in this state in a tic-tac-toe game and you're playing X. So what you can do, you could place an X here, you could place 1 here, you could place 1 here. These subsequent states are listed in here in this tree. And from that state on, player 0 would have the turn. So he could put here a 0 or here, and these are the following subsequent states. So this Monte Carlo tree search builds up this look-ahead tree, what could possibly happen in the future. And what it does, it also assigns a value to these states. And these states encode how good is the subsequent state. So in here, -1 means we lose, and +1 means we win. So if you're here placing an X here, you basically lost because 0 could just put a 0 in here and win then. But in case 0 decides to put a 0 here, then you win suddenly. So you get a +1 for this state here. And then, yeah, the game turns out in your favor. But so in the end, we only take an action for this state. So in the current state, what would be probably the best outcome for us? And in this case, this if we place an X here, we can always get like a draw here if we play perfectly. So that would be the action to take in here. So of course, in real life, things are not as simple as a simple tic-tac-toe game. And these look-ahead trees just grow very fast and they get very big. So it's not feasible to do like an exhaustive tree search to go through all of the states. That's just by computational boundaries not possible for most applications. So what Monte Carlo tree search tries to do is build that look-ahead tree asymmetrically and go more into detail into states that are likely to yield better results. So where the values that we estimated are higher. So in here, you could probably think that around in this region, there are pretty high values for the states. And here is probably an even higher value for states. So if you're trying to take a decision here, you would probably go this route here because there's probably, yeah, the best states lie around here. So how does Monte Carlo tree search come up with that tree? So it repeats a 4-step process, which consists of selection, expansion, simulation, and backpropagation. So at first you start like only with a root node, and then you successively add nodes to the tree, and you do it like so. So first you just navigate to a leaf node. So in this case, we could navigate here. How you navigate through the tree is called the tree policy. Then when you reach that leaf node, you look into one step into the future and expand the node. So you look what could be a subsequent state and add it to the tree. So here, this could be also multiple trees, multiple states. I only in the visualization added one. And then what you do, you evaluate how good is the state. That you do by a default policy, which basically, if you're in the game, it would just play the game randomly to the very end and then just write the result in here. And then you backpropagate the result up the tree, just like, as you saw in the tic-tac-toe. So, and also like how you play the game out could be random. You could have rules, or you could just have a more sophisticated AI technique to determine that value. So with that policy or with this approach, how will it look like in the CRF allocation example? So you would start in at the beginning with an empty schedule and then successively add just these rectangles into the Gantt chart. And then once you have added one, you would then look ahead what could the next state possibly look like. And then if you have an objective function that tells you how good is a already done schedule. So in the very end, you can propagate that up. So which is just exactly this process here. And this is just a visualization how it would look like in layer 1. But you could just do exactly the same thing in principle for this second layer. That's just one possibility how we could extend things in future, and one that I'm really excited for. But now let us transition to questions and answers.
So first of all, thank you to Sylvia and Alexander for this interesting presentation webinar. And then the stage is open for questions from the participants. Anything unclear, anything we need more information about? I assume everything is clear. You explained everything perfectly. So there cannot be any questions. Then I say thank you from my side. Thank you for joining. And then the last word is for Alexander and Sylvia if they want to say something at the end.
Yeah, I would also like to thank you for joining to our webinar. Even
Yeah,
though
thank
it
you.
was fun.
Yeah, I hope you had
And sorry
fun.
for spam.
Then thank you very much, everyone, and see you hopefully in the next webinar, end of January. Bye.